Hello guys, welcome to 7th lecture, meaning that it's our 8th video. In this one I'm going to talk about probabilities, which we covered in class today. Before I start talking about solving exercises, I'm just gonna run through the definitions, because this topic is pretty much relies on the definitions and on theoretical part. So once you get that, actually you can go to solve the numerical problems. So let's see. First, what is probability? It is just the chance that event will occur. Range of a probability, it lies between 0 and 1. And probability can be written as percentage as well. So usually you would get a number 0 point something, and then you would multiply by 100 in order to get the percentage. So the experiment or the random experiment is the occurrence of only one outcome. Simple space is set of all possible outcomes of the experiment. Elementary event is the specific outcome of an experiment, and event is a collection of one or more outcomes of the experiment. I'm just reading it now here. I'm not gonna explain them like in details because we will see them through the examples. I think it would be much easier if I just show them to you through examples. And now three really important ones. So mutually exclusive events. These are the events that cannot occur at the same time. So for example, elementary events. We will see in the example what they actually are. Collectively exhaustive events. At least one event must occur when an experiment is conducted. The complementary events are events consist in the negation of another one. So basically the examples would be mutually exclusive and collectively exhaustive events. The notation for complementary events are usually written in these two forms. Either will be correct, and we will see through the examples in a minute how to calculate and what actually they are. So let's start first with some probability types. So let's start with the classical theoretical probability. So let's go like this. So let's say that we roll a fair dice. And what does fair dice mean? It means that there is a same percentage of chance that you will get one number on it. You know, there's no, let's say, mistake on a dice. So let's see. How will we find the probability that we will score 1 on when we roll a dice? So we would, let's take a look. So we would divide the number of favorable outcomes with the number of possible outcomes. So in our case, number of favorable outcomes will be 1, right? And the number of possible outcomes will be 6, because dice has 6 sides. So we would write that when we roll a fair dice, we would have 1/6 possibilities to get 1. And now let's take a look for the other one. So 1 or 6. So what would we do? We find the probability for 1/6, we find probability for 6, and then we just add them together. So we'll have 1/6 plus 1/6 to be equals 2/6, which is simplified 1/3. Now let's take a look at this. Possibility of scoring 2 and 3. In this case it will be 0. Why? Now we are coming back to the idea of mutually exclusive events. When you roll a fair dice, you can get only one outcome. You cannot get 2, 3 or more at the same time, right? So if you roll it once, you will get only one number and that's it. So in this case, the probability that we would score 2 and 3 will be 0 because the events are mutually exclusive. What's the probability of getting even number? So what are even numbers? 2, 4, and 6. So we have 3 even numbers divided by 6 will be 1/2 or 50%, as we said that we can write them as percentages as well. What would be the probability of rolling a number that's less or equal than 2. So what are the numbers we can get in that case? 1, where's my finger? Okay, 1 and 2. So we would have again written 2 over 6, which will be 1 over 3 when simplified. And the probability of scoring bigger or equal than 3. So we have 3, 4, 5, 6. 4 possible outcomes, 4 favorable outcomes, sorry, divided by 6 possible outcomes would give us 2 over 3. Good. When talking about this theoretical or classical probability, I also want to take a moment and talk about intersection and union. So what is intersection and union? And we usually present it as a Venn diagram. So let's take a look at these two sets of number. So set of X consists of numbers 3, 12, 5, and 13, and set Y consists of numbers 14, 15, 6, and 3. So let's first find their union. When we get the exercise, and when it says like this, X or Y, we know that we're going to find their union. And what is that? They're just all numbers from these two sets, or any sets that you get. Doesn't matter, you can get as many sets as possible, just combined together. And when combining, when you have common elements, you don't write them 2, 3, or more times. So let's say, what is it going to look like for us? So union of X and Y will be set that consists of numbers 3, 5, 6, 12, 13, 14, and 15. Okay, so you noticed that we have number 3 in both sets, but we didn't write them 2 times. We just wrote them once. Okay, and now we're gonna look at the intersection. X and Y is our intersection. So, and the notation is for union is this U, and the notation for intersection is our reversed U. And that's basically the common number. Okay, so the number that's same for both sets, and that is our number 3. When we present it on diagram, and I need to say, guys, that there is a mistake here. Okay, so this is not union, this is intersection. So instead of having this U, we would have this U. I'm very sorry for making that mistake, so just don't confuse yourself, please. So we would say that common elements belonging only to the set X, in this case, will be 12, 5, and 13, and we write them in this little circle. 3 as a common element, which means our intersection. So once again, this is a mistake, will be here in the place where these two circles intersect each other. And these are the values that are only found in a set Y. So 14, 6, and 5. And that will be pretty much about the intersection and union. We will come back to this idea a bit later when we start talking about rules. Now I wanna explain a bit the difference of the sets or relative complement. So what is the difference, and how would we write the difference of the set A and B? So easy, just A minus B. It can be written as A minus B, it's totally correct, or it can be written with this straight line, and you will know that that's actually just a minus. So and example, so this is how would we say this. So find a set of elements that are in set A but not in set B. So that telling us it will be A minus B. So let's find it. Let's find it for these two sets, which are exactly the same sets that we used in this example. So once again, for X we have values 3, 12, 5, 13, and for Y we have 14, 15, 6, and 3. So let's find a set of elements that are in set X but not in Y. So X minus Y. And we will have 3 and 3 cross each other out. We have 12, 5, and 13. And please note that in this case we do not write 14 and 15 and 6 as well, okay? Because we just assume that they disappear. So don't write -14, -15 because it wouldn't be correct. And now let's find the set of elements that are in set y but not in set x. So basically y minus x. We would have 14, 5, and 6. 3 as a common element in both sets cross out. And what would be the set of elements that are in set x but not in set x? That doesn't exist, right? It's a null set. So we would just write 0 and cross it, because x minus x will just give us null set. There's nothing left. And lastly, I want to talk about universal set. So if you remember, like a minute ago, I spoke about this complementary event. Well, this is exactly the universal set. So probability of A can also be found as by writing 1 minus the universal set of P of the probability of A. And what is the universal set in this case? What is this probability of universal set of A? It's basically everything that's not A. Okay, so what would be the universal set of X? It will be everything in the universe, and literally in the universe, that's not X, that doesn't belong to the set of X. So, for example, number 7, number 300, me, this pen, everything literally that's not already in the set of X will be in the in this set. So this is also sometimes convenient to write, and we will take a look at it in a minute. Now let's move on to the experimental empirical probability. It is the estimation of something happening based on the experiences from the past. And please note, when we're talking about these probabilities, there is another type of probability that we will look at in a second. The first probability that we've done, which is the theoretical or classical probability, is the most accurate one. Okay? And the probability that you find based on this classical one is the most probable one to occur, let's say like that. Okay? While experimental one, you don't know if your estimations will be correct. You don't know if your estimations are going to happen. But you make them based on something that happened before in the past. So let's take a look at this chart. It's representing the number of games and points scored per game. So let's say basketball game, doesn't matter. And estimate the probability of scoring more than 30 points on the next game. So here's the number of games and here's the number of points. Okay, so first we would need a total number of games. So let's calculate. We'll just read it from the bar chart. I think that all of you are familiar with it. So we will write 2 plus 4 plus 5 plus 3 and plus 2, which will give us number 16, meaning that there were 16 games played in the past. And now, knowing that, we ask ourselves, so what is the probability of getting 30 or more points on 17th game? Right, on the next game. So let's take a look. Let's take a look at the probabilities of scoring 30 or more points. So here and here. So these are two areas that we're interested in, right? And we will see the number of games where we scored between 30 and 39 was 3, and number of games where we scored between 40 and 49 are 2. So we would write that our probability will be 2 plus 3 divided by 16, which would give us 5 over 16. And we would say that the estimation, that the probability that we would score 30 or more points in our 17th game will be 5 over 16. Once again, is it going to be a correct estimation? We don't know. Okay? But it is our estimation. And the last type of probability will be subjective probability, literally meaning estimation of something happening based on pure guessing. In other words, based on nothing. So what is the chance of scoring 1 on the final math exam? 1 over 5, right? Because there's one grade that you can get, there are 5 possible grades, just 1 over 5. Do we know that we'll score it? We don't, but we're hoping to. So that's pretty much it. I will not talk about the subjective probability, and I will move to probability rules. So let's see when it comes to a bit more complicated and complex questions, how would we solve them? So first we're going to look at the addition rule, and we're going to go straight into example because there's not that much theory that I can say about this. So take a deck of cards. Each deck has 4 suits, and each suit has 13 types of cards. So we have A, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, K, and Queen, Q. Random cards are picked from the deck, and we need to estimate the probability that our card will be Jack. So 4 over 52. Why? So we have 4 suits, meaning that there are 4 jacks. The number of cards in each deck is 52. So we would say that the probability of getting a jack is 4 over 52, or when we simplify it, it's 1 over 13. Probability of getting heart, 13 over 52. Why? Because heart is type of card, and there are 13 types. And when we simplify it, it will be 1 over 4. Now, what is the probability of getting jack and heart? It will be 1 over 52. Why? Because in one deck there's only one card that's jack heart. There's only one jack heart in the deck of 52 cards, right? So it's 1 over 52. And now the interesting part comes. What is the probability of scoring jack or heart? Okay? And our addition rule formula says probability of set A or B to occur will be equal probability of set A plus probability of set B minus probability of set A and B. And if you remember what I told you about the intersection and union, our probability of set A and B is actually our intersection. So how would we now, knowing that and representing it in Venn diagram just to make it a bit clearer? So here are jacks, here are cards, and here is their intersection. So our jacks and hearts. So how would we now calculate this? Well, easy. So the number of jacks plus the number of hearts minus the number of jacks and hearts, meaning that 4 over 52 plus 13 over 52 minus 1 over 52 would give us 16 over 52, which is equal to 4 over 13, which means that it is the probability of scoring or picking jack or heart is 4 over 13. Okay, that's pretty much it about this rule. I think it's really easy. I think it's really straightforward, so I'm just gonna move to the other one. Basically, when you see word or, you know it's addition rule and that you need to use this formula only in case when events are not mutually exclusive. So if events are mutually exclusive, that means that they cannot happen at the same time, meaning that there will be no intersection. In that case, nothing special, we just ignore this part. Number of jacks and hearts in this case, we will just write number of jacks plus number of hearts. We would get the correct answer for events that are mutually exclusive, of course, not for this example. But yeah, it's probably. Now, having that said, I'm gonna move to the multiplication rule for the independent events. So the multiplication rule for independent events formula is this. So probability of A and B, set A and B to occur will be probability of set A times probability of set B. So let's take a look at the example immediately. So flip a coin 2 times and estimate probability of scoring 2 heads and probability of scoring tail, head, tail. Now let's first realize, why is this independent event? Because no matter what you get when you flip coin once, it will not influence what you get when you flip it second time, fifth time, or any time. Okay, there's always 50% of chance for flipping a coin and getting head or tail, and that's exactly what I wrote here. There's literally 0.5% or actually 50% of chance of scoring head and scoring tail. When you flip coin 2 times, you have 4 possible outcomes, right? You can get 2 heads, you can get head tail, you can get tail head, and you can get 2 tails. So let's see now how would we solve it for 2 heads. So we would multiply probability of scoring head and on the first flip, and the probability of scoring head on the second flip. So 0.5 times 0.5 equals 0.25. And let's say we flip it third time, and what would be the probability of scoring tail, head, tail? So just same way, 0.5 times 0.5 times 0.5 being equal to 0.125. Now let's flip a coin 3 times and estimate the probability of scoring at least one head for these 3 flips, not getting all tails, and at least one head in 10 flips. Okay, so first and always when you have the coin question, always find the number of outcomes and even write them down. So for flipping a coin 3 times, there are 8 possible outcomes which are presented here. So you can get 3 heads, you can get head, tail, head, you can get 2 heads and tail, tail, 2 heads, tail, head, tail, 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 head, 3 tails, and head, tail, tail. So you have 8 outcomes. And what is the probability of scoring at least one head? So it would be 7 over 8. Why? Because there's only one outcome in which you don't score heads at all, and that's where you score 3 tails in a row, right? So it's 7 over 8. What is the probability of not getting all tails? So how would we now write the probability of not getting all tails? Let's take a look at first at our outcomes. What is the probability of getting all tails? It will be 1 over 8, right? Because in these 3 flips you can get 3 tails only once, right? So the probability of getting all tails will be 1 over 8. And how would we write this and find the probability of not getting all tails? It will be just 1 minus the probability of getting all tails. So 1 minus 1 over 8, and we would get 7 over 8 because there are 7 possible outcomes in which we didn't get all tails. And lastly, probability of getting at least one head in 10 flips. So we would write as this: 1 minus probability of 10 tails in a row, and we would solve it. So 1 minus 1 over 2 to the power of 10, right? Because we are multiplying it 10 times, and we said that the probability of scoring one head is 1 over 2. Will be equal to 1 minus 1 over 1024, and that would give us around 99.9%. Okay, I hope that this was easy. Now we're going to take a look at the multiplication rule for dependent events. So the formula for this one will be a probability of a set A and B to occur equal to probability of set of A to occur times the difference between set B and A. And we've covered this just a couple of minutes ago, so I hope that you remember this. It's just set B minus set A. And now let's take a look at the example immediately. So you have 8 coins in a box, 3 of them are unfair and have a 60% of chance of coming up heads when flipped. Coin is randomly chosen from the box and flipped 2 times. What is the probability of getting 2 heads? So this is our little drawing, this is our little box. It has 8 coins, the 3 red coins are unfair. And the most convenient way to represent this is using tree diagram. So we would flip a coin. we have 5 over 8% of chance to get a fair coin and 3 over 8 unfair. Why? Because we have 5 fair coins and total is 8 coins, so 5 over 8. It's important for me just to mention that when you add these two numbers from these two branches, they have to give you 1. So be careful not to kind of mess up with that. Okay, once you took fair coin, you have 50% of chance getting head and tail, and once again, in case you get a head, 50% of chance of getting head and tail on second flip. So this is first flip, this is second flip. And now let's take a look at the unfair coin. You have 3 over 5% or 3 over 5 chances to get a head because it's unfair, and 2 over 5 chances of getting tail. And once you score, once you get the head in a first flip, for unfair coin you would flip again, and the probabilities will be exactly the same. So 3 over 5 for head and 2 over 5 for tail. Now when you have it written like that, we can see now what we are actually looking for. So our question is, what is the probability of getting 2 heads? So we need to focus as it follows. So for the fair coin, we have 2 possibilities, and for unfair one as well 2. And how will we find the probability of scoring 2 heads if the coin is fair? So we would multiply 5 over 8 times 1 over 2 times 1 over 2, and it would give us 0.15625. We will do the same thing for unfair coin, so the probability of getting unfair coin and times probability of getting head and times probability of getting head. So 3 over 8 times 3 over 5 times 3 over 5. It would give us 0.135. When you have these two values, you will just simply add them, and that would give us 0.29125. It's exact number from my calculator. And our answer will be that the chance of scoring or flipping 2 heads in this game will be 29.13%. Guys, that's all from me for this lecture. I hope this makes sense at least a bit. Please practice. This is not really hard. And if you have any questions, don't hesitate to call me. Other than that, I'll see you in the next video. Stay safe.